now we will be considering the electric field of a charged wire. And as we have seen in the figure, the wire extends along the x-axis, and so this is the x-axis, this is the y-axis, and it has a length L. So the coordinates of this is x equal point is end is x equals a, and the coordinate of this point is x equals L plus a. Now it carries charge that is distributed uniformly over the length of the wire, and so the linear charge density lambda in this case is the total charge carried by the wire divided by the length of the wire. So this is what is given. This distance is also given, and we are requested to find what is the electric field of the charge spread over that wire at a point P, which is the origin in this case. Now, we have a standard algorithm that you can apply to all problems of this type. Now, by doing this, I will be highlighting that algorithm, the steps of the algorithm. If you follow it closely, it is almost the same for all problems of finding the electric field of continuous charge distribution. And also, actually, when we move to the electric potential, it is more or less the same when you try to find the electric field, electric potential of continuous charge distribution. The first step is to find what is the dq here. Well, evidently, the major idea in finding the electric field of continuous charge distribution, as we have described, is to split the charge distribution into small elements dq. So evidently, here, the length of the wire will be cut into small elements. Each of these will be the dqi, and then you will be finding the electric field of each one of these. And then add them up to find the electric field at the whole wire here. But adding up means integration, as we will see. So we take any of these as our dq. We choose an arbitrary point in this case. So take this, for example, and this will be your dq. Now, while the analysis that we are going to do is almost the same for the positive charge or negative charge, apart from the flip in the direction of the field, at some point, when you want to determine the direction of the field, you have to specify the direction, the sign of the charge. So for definition, I assume that the charge here is positive. And therefore, this dq will contribute a field that I call dE. So the first thing, find this dq, and then find and draw the arrow of dE. dE is the field of dq at the point P. Well, this is a positive point charge in a way, and so it will contribute a dE here. So now we know, okay, this dq will contribute a field, and this field will be in this direction. This is the first thing that you do. The second thing is you try to see what happens before doing calculations. You can do some qualitative arguments, and to get an idea about what will your answer, how will your answer look like, or what will be the general features of the electric field that you will end up with, even before doing calculations. And this point is called, or this procedure is called, making use of the symmetry of the problem. So here, we'll say, okay, this is the field of dE. So what will I get when I add up the dEs of all the dQs? This, when I integrate over the whole wire. Well, evidently, each of these dQs will contribute a field, dE, of its own in the same direction. Okay? So when I add up all the fields, the total electric field of the wire, E, will be again, for positive charge, will be again in the along in this direction, so along the negative x direction. Okay, this is I find out without still doing any calculations. Okay, these ideas are called usually conceptualization of the problem. So you conceptualize the problem. Of course, at the beginning you just have to have a mental picture of it and then draw it. We have already done this. Then dq, what is the field of dq? What does dE? What does symmetry tell me about the final E when I add up all these dq's? So this concludes the first part of the analysis of this problem, which is conceptualization. The second is doing analysis and proceeding with the solution. And the first step in this regard is you'd write down an expression for dq, the electric field by for dE, the electric field by dq. And so you say that dE in this case, and you write it as a magnitude, is equal k dq over r square. Now this is the general expression. Okay, what is r? R in this case is this, for this specific dq, it is r. Now what you do is you try to express this r in terms of the variables given in this specific problem. In this particular example, evidently our r is actually x, the x coordinate, because r is this distance and it is the x coordinate of dq. So this becomes k dq over x squared. Now after that you express dq in terms of the charge density. Okay, and as we have learned, because this is a linear charge density, usually dq is equal the linear charge multiplied by the length over which it is extended. This is, if you go back to the lecture, then you will see that if dq, which is the charge extended or on a part of the wire of length L, dl, is equal the linear charge density multiplied by this dl. Now you do this here, but you express also, rather, dl is a generic variable for any wire. Now you specify to the expression that, to the coordinates that you have in your problem, and you know that this quantity, in this case dl, is nothing but dx. So therefore I write this as k lambda. Lambda is constant now because this charge is uniformly distributed over the wire, and dx over x squared. So this is the expression of dE, the electric field, the magnitude of the electric field that is due to this dq. Now note that I have written dE here as a magnitude. I forgot about its vector nature, although it's a vector. Why is this? Because I know from the symmetry of the problem, the arguments that I have just made, is that all the dE's of all the dq's are in the same direction. So I know already the direction, so I forget about it. Okay, and then I put it by hand when I find the last expression. So now, having identified this, now I add up, I set up the integral. I say that E in this case, the modulus of the electric field, is equal integral over dE. You sum the electric fields of all of these, and what is this? This is integral over k lambda dx over x squared. So you have set up an integration. Why? What does this mean? This means that I am adding up the contribution of all dq's, summing the dE's of each of these dq's. Okay, and this amounts to doing this. Okay, now at this stage things start to become clear. I mean, what is your integration variable? You are integrating over what? Things start to become clear here. Usually this quantity actually is a hint that, okay, it seems that the variable is x, which is what you expect actually. Now, what remains is to first fix the limits of integration and proceed. So what are the limits of integration? Since my integration variable is x, x varies from where to where, okay? Now, from where to where, actually, the limits of the integral should be selected so that they cover the charge, the region, or in this case, the length where the charge is distributed. Now, x is a variable which goes from minus infinity to plus infinity. But in my specific case, I want to sum over all the dq's. So I should limit the limits of the variable to the part of the x-axis where I have charge. So what is this part? Well, it is x equals a to x equals L plus a. So I put the limits x to L plus a. Okay? The coordinate of these 2 points, the x coordinates of these 2 points. Now, I want to integrate. I note that k lambda, of course, in doing this, again, I emphasize that you must check that with these correct limits, when you are actually integrating, you are physically summing over the contribution of all the dq's. So you are covering the whole charge. Now, we proceed with the integration. Sometimes you might need to do some change of variable at some point, but at this point, you don't need to do that. So you just proceed with integration, and you say, okay, E in this case, you note that k and lambda are both constants, so you take them outside the integral over x to L, sorry, it's not from x, it's from L here, or from A, not from, sorry for this, from A to L plus A. Okay, so this is are the limits, and you will have dx over x squared. Now this is quite a simple integral. Even if you don't know it, you can find it from tables if you're still not good enough with integrals, but it is easy to find it. The integral of 1 over x squared, which is x to minus 2, is minus 1 over x. So this becomes minus k lambda 1 over x between a and L plus a, and this gives us for the integral k lambda 1 over a minus 1 over L plus a. Minus 1 over a, yes, plus 1 over L plus a. Is that correct? The upper limit is L plus a, the lower limit is, and you have a minus between them. Minus minus is plus, so that's your integration. You can, by doing this, you have got an expression for your electric field. Now we come to finalize. By finalizing, first you check that things are correct and you have not made a mistake. The first thing is you check that this expression is along. Now we finalize things. Finalization means you have first to check that you didn't make a mistake, and then find another approach to finalizing things is to investigate your expression in a given limit where you know what it should look like, and then see that if really it reduces to the expression that you expect it to reduce to in that limit. So we start with checking first that things are correct. The first check might be to see if this expression is really in the negative x direction. And to see this, let me have a common denominator here, and if you do this, you will have your E equals K lambda. The denominator will be A times L plus A, and multiplied. The first thing will be minus L minus A plus A, and this will be minus, these will cancel, minus K lambda L divided by A times L plus A. Of course, I have I hat here, I hat here. So this expression evidently is an expression, because everything here is positive, is an expression along the negative x direction. So it gives you the right direction at least. Now the second thing is to check limits. How to check the limits? Usually you have the following criteria for the electric field of any charge distribution, which comes from the dimensions of the electric field of a point charge. Now, the electric field of a point charge goes like kq over r squared. So it is k, the units of this, or dimensions of this, are k times Coulomb divided by length square. So any expression for the field you get from any charge distribution, even if it's not a point charge, should look like the k, Coulomb's constant, multiplied by Coulomb divided by length square. Now, this is true because, you know, even if the distribution is not, if the electric field is not due to a point charge, it is the superposition of electric fields of point charges. This is how we find the electric field of continuous charge distributions, and so therefore the limits should be the same. It should look roughly the same. So let's check that this works. Now k, now here lambda has units of Coulomb per length. Coulomb per length times length is Coulomb. So you have Coulomb here, and here you have length times length, which is length square. So indeed you have Coulomb multiplied by, k multiplied by Coulomb divided by length square. Actually, you can even re-express things in terms of Q, which is the charge, because now it's a finite charge, which is the charge distributed over the whole line, by expressing lambda as Q over L. So if lambda is Q over L, then lambda is Q over L, then this L cancels this L, and you get your expression as minus KQ over A times L plus A along the I hat. And this is now explicitly of the form K multiplied by Coulomb divided by length square. So this is the another check that your expression is at least correct dimensionally. Of course, being correct dimensionally doesn't mean it's correct, but if it's wrong dimensionally, you can go and check again. Okay. Now, the last check will be to consider a limit that of this expression, so that the system reduces to a system that you know its answer, and find if it really gives you that expression. So for example, if you look at this field here, now if you take this to large distances, that is, if you make A much larger than L, then in this case, from the origin, this line will look like a point charge at a distance A from the origin. So the electric field will be KQ over A square. So let's check that in this limit, our expression will reduce in this limit to the KQ over A square. So consider the limit when A is much greater than L, or L is much less than A, so that L over A is much less than 1. Now, in this case, E, you can write it as, take A outside, it will be A square 1 plus L over A, I hat. Now, this reduces when L over A is much less than 1 to find the limit when L over A is much less than 1. What you do is you ignore this in comparison to 1, because this is what you are saying. L over A is much less than 1. So you ignore this in comparison to 1, and you get this as minus KQ over A square along I hat, which is exactly the expression that you expect, the electric field of a point charge, and it is pointing in the negative x direction. So now you are confident that your expression for the electric field is correct.